Good morning everyone. Today I am going to explain you about the advanced NMR technique, that is FT-NMR. I am Dr. Karthik Rao, Assistant Professor in Department of Organic Chemistry, Gayatri Vidya Parishad College for degree and PG courses. Before going into the advanced technique, that is FT-NMR, I would like to share you about the continuous wave NMR. So what is this continuous wave NMR? This continuous wave NMR, if you see the experimental procedure of this continuous wave NMR, the sample is taken in the sample holder and two magnets are kept constant. The radio frequency is continuously increased or decreased or continuously passed through this sample holder. That means the radio frequency should match the nuclei which are present in this sample, such that we had continuously change the radio frequency each time that matches the sample here will be recorded in this amplifier, and we get the graph. So this is the basic experimental procedure of the continuous wave NMR. But this has a lot of disadvantage, as it takes a lot of time, because each and every proton should be excited using this RF value and should be recorded. So in order to decrease the time consumption, or in order to reduce the power of RF frequency, a new technique called as Fourier transform NMR has been evolved. So what is the advantage of this Fourier transform NMR? Is it takes very less time, almost seconds. Why that less time is required? As the instrument itself, if you see this instrument, it has a sample holder and the same magnets here, but it has a something called as pulse switch. So what is this pulse? Pulse is a short duration of RF frequency which is emitted by this RF generator, a very short duration, that is about 10 microseconds, which is sufficient to excite all the nuclei present in the sample. Then this RF is recorded or received by the amplifier, and then it is detected by the detector. But here something new called as Fourier transform, a computational program or a mathematical program which is kept in the computer, which receives this time domain spectrum. So here we get a time domain spectrum from this RF amplifier, and this time domain spectrum is converted into the frequency domain spectrum, and we will get a graph finally. It looks like a simple thing, but it has a complicated things. So before that, this is the graph which we get from the spectroscopy, but it is the time domain spectrum. So this has to be converted into the frequency domain spectrum by using the Fourier transformer. So this is how it is converted. So this is the time domain spectrum, which is then converted into the frequency domain spectrum. This is how the FT-NMR works out. But before going into this detail, I would like to share some theory behind the NMR spectroscopy. So first of all, how a nuclei can be excited. So nuclei present in a molecule will be revolving around itself with some momentum. But if we take it in the XYZ direction or axis and pass external magnetic field B0 in the direction of Z axis, okay, so where the external magnetic field is applied along Z axis. Now what happens? The nuclei will be splitted into two. One has higher energy, one has lower energy. These are called as alpha and beta states. Okay, whenever a external magnetic field is placed along the z-axis, what happens immediately? The nuclei will be split into two halves, that is alpha and beta states. Alpha is the lower energy, whereas beta is the higher energy. Now, how they revolve? They has a new rotation called as Lamar frequency. I will show it in the next slide. But this representation is called as classical picture representation. Whereas coming to the quantum picture, it also says the same thing, but the representation is different, which has, see this is the z-axis and we are passing the external magnetic field through the z-axis. So it has two different states, that is alpha and beta state, which is higher and lower energy. So the alpha state is lower energy, whereas beta state has the higher energy. So this type of representation is called as quantum picture. So now we have two types of representations here. Then we go to the spinning of the nuclei. So I have already told you that whenever a external magnetic field is applied, the two states will be forming and they has a new frequency called as Lamar frequency. So this is for a single nuclei. So on the Lamar frequency, that is denoted by omega, is equal to gyromagnetic radiation into B naught. So the gyromagnetic ratio will be will have for each and every nuclei, and B naught is the external magnetic field. So this is the property of the nuclei, and this is the field which we are acting. So now this will be precise, or this will be rotating around the z-axis in this new circle. So this we have taken for a single nuclei. But when we see the molecule or when we see the compound, if we see our sample, they have lot many nuclei. So whenever we give the B naught or external magnetic field, we observe many nuclei that are revolving around this Lamar frequency. This is for a large number of nuclei. So you can see the difference between these two alpha and beta states. The alpha state has a larger population, whereas beta state has the lesser population. Why? Because the alpha state is lower in energy, whereas beta state is higher in energy. Thus, these two states can be differentiated, and thus we get a NMR signal. Only when the Boltzmann population distribution is difference is there, then only we get a NMR signal. So that is why we are getting a NMR signal now. But this representation, we cannot take it as a single each and every nuclei into the consideration. Therefore, yes, vector quantity of these all nuclei. So we can add up all, this has all the same Lamar frequency, therefore we can add up all the nuclei present in a molecule. That is called as bulk magnetization. So this bulk magnetization is represented as a thick arrow, which is represented as a thick arrow along the direction of z-axis, because the B naught is passed through the z-axis and this is revolving around the z-axis. Therefore, we can represent this bulk magnetization along z-axis. So this is called as bulk magnetization vector. This is a vector quantity which is add up, which is the addition of all the individual nuclei present in a molecule. So now we get a bulk magnetization vector. So now from now onwards we will deal only with this bulk magnetization vector. So now we have a bulk magnetization vector. That means we have our nuclei. We have to pass a RF radiation to it. So where should we pass? From which direction the RF radiation should be passed? The RF radiation should be passed perpendicular to the direction of the nuclei. That means if the nuclei is present in the Z direction, then we have to pass our radiations through X or Y axis. Therefore, I will take the direction as a y-axis. So this is the y-axis, and this is the wave RF radiation. So this wave should match the Lamar frequency. That is why we are giving this Lamar frequency as omega naught is equal to gyromagnetic ratio into B naught. So this frequency should match this frequency. Such radiations will cause the excitation of the nuclei. So how can we look this? So this will be, if you observe this one from here, if a person presents here and if we observe here from here, then what happens? These waves will be looking like a circular. So you can see that this wave is looking like a circle. So that is called a circulating wave. And the direction of the circulating wave is along y-axis, because we are passing the circulating wave along the y-axis. So we can see the y-axis as a reference. So the RF is passing through the y-axis with a circulating wave. Okay, this is called as circulating wave. Now, when we pass this circulating wave along y-axis, when this magnetization, bulk magnetization is rotating along its Lamar frequency, what happens? So this is the Lamar frequency, and why now we are passing this RF along the y-axis. So circulating wave. Okay, now what happens? Due to this effect, we get a new term called as B1, that is bulk magnetization, external magnetic field. A new magnetic field has been appeared here. So what happens to this? If we see this same thing again, see, this is the bulk magnetization, which is rotating along the z-axis with the Lamar frequency. Now we are applying the RF along the y-axis with a circular wave. So whenever this circular wave and this Lamar frequency matches each other, that means resonance has been appeared or excitation has been taken place. That state is called as precision. See that? So new path has been appeared. This is called as precision. That means this Lamar frequency or this nuclei is looking this wave in a rotating frame of reference. So this is called as rotating frame of reference or precision. So now we have a new terms called as omega 1 equal to gyromagnetic ratio into B1. So this is the new one, new free precision. This is also called as Lamar precision. Okay, this is also called as Lamar precision. So now a new path has been appeared for the bulk magnetization. So now it revolves around this one. So what happens here? I am just repeating again that the bulk magnetization, whenever we take a bulk magnetization in z-axis and we pass the RF along y-axis that is perpendicular to this bulk magnetization with a circulating wave, what happens? This Lamar frequency, this is the Lamar frequency and this is the circulating wave. Both sees each other, and whenever they match, the frequency between these two matches, a new frame of reference will be appeared. This is called as precision or rotating frame of reference. Now the bulk magnetization takes that path. So what happens now? We are giving a RF pulse. What is meant by RF pulse? The frequency which is given to this bulk magnetization is called as RF pulse. So how much pulse is that? Whenever we apply the RF pulse, what happens? The bulk magnetization vector will come into the x-axis. Why this is coming into the x-axis? Because we are hitting this in the RF pulse such that the angle between these should match and it should come to the x-axis. Why this is coming to the x-axis? Because our detector is present here on the x-axis and we are detecting this signal at x-axis. So this bulk magnetization vector will come to the x-axis. This is called as RF pulse. Okay, so the RF pulse is applied along the y-axis with the frequency, so that the bulk magnetization vector along the z-axis will fall onto the x-axis. So new reference is that. So now we should see the experiments of the pulse. So this pulse is required to excite all the hydrogens present in a molecule. So how we vary this pulse? There are different types of pulses. For example, if we give the RF radiation for the bulk magnetization with a time period of pi by 2 by omega 1, that brings the bulk magnetization to the x-axis. Okay, so it's from z-axis to x-axis. The angle of this deviation is called as 90-degree pulse. That means the magnitude of this, all the bulk magnitude is bending at a 90 degrees towards x-axis. So such that we are giving the pulse at a time of pi by 2 by omega 1. This is the time required to give, or this is the time required for a switching on and switching off of a RF radiation to excite the bulk magnetization from z-axis to the x-axis. So this is one type of pulse. This is called as 90-degree pulse. If we use lesser time, it will go for a 45-degree pulse. Then it will come to the y-axis. Suppose we use a more time or larger time, that is t is equal to pi by 2, pi by omega 1. Then it will come onto the z-axis opposite to the direction of the bulk magnetization, which is present in the first phase. So here it is in the negative state. So this is the positive state and this is the negative state. So this is called as 180-degree pulse. That means we are giving a 180-degree pulse such that the bulk magnetization reaches the z-axis in the opposite direction. So these type of pulses are called as 180-degree pulse. So we can vary different pulse according to our experimental procedure, or according to the experimental given, or according to the molecules. So that I will discuss in the later classes. But before knowing that, what happens to the bulk magnetization which is present in the x-axis now? Now we can see that whenever we are applying the radiation along the y-axis, the bulk magnetization vector will come into the x-axis. So this is called as excitation as per the mechanics, classical mechanics or quantum mechanics. Now after the excitation, what happens? The nuclei again reaches into the original position. That is called as relaxation process, or it is also called as decay of the magnetization. So how it reaches? It goes back to its original position like this. So it goes back from the x-axis to the z-axis and increases in the direction of z-axis. So it decreases in the direction of x-axis and increases in the direction of z-axis. Here we can see there is a detector here present at the x-axis. So it detects the signal. When it reaches the x-axis, it detects the signal where it has the highest intensity, and slowly the intensity will decrease. Now the intensity will increase in the z direction. So the detector senses this intensity from x-axis to the z-axis. This is called as FID. I will show you. So this is the called as actually relaxation process. So relaxation process is of two types. So what is the relaxation? From x, it should reach z. Simply called as relaxation. From x-axis, when it is excited, so first it comes from z-axis to the x-axis, again it reaches the z-axis. That process is called as relaxation process. It is of two types. First one is T1 relaxation. Second one is T2 relaxation. So T1 relaxation is a building up of the magnetization along z-axis. T2 relaxation is the decay of relaxation along xy plane. So these are the two processes where relaxation will be performed. We shall see both the. The first one is T1 relaxation. It is also called as spin lattice relaxation. So where I have shown you earlier that in the x-axis direction it decreases, whereas in the y-axis direction it increases. So you can see this one. So this in this direction the x-axis it has decreased. Previously in x-axis it is the most intense. So now a detector is here. So you can see that at starting point the intensity of x is more, whereas slowly it will decrease and the z-axis intensity will be more. So the detector will detect the intensity at that time interval. So at the first point or first second it is more, whereas slowly the time decreases and the time of the relaxation process increases or the time decreases. What happens? The intensity of the x also decreases. Therefore, the detector will detect this one, the intensities at points. So this is called as spin lattice relaxation. So another relaxation is there that is called as spin relaxation, very important one. So this is also called as T2 relaxation. So where the same x axis point will be released towards xy plane. Previously in T1 relaxation it has decayed along z axis, that means x axis and z axis, but in this relaxation it is decaying along the xy plane. Therefore, see, this is the process where it will reach. So the decay or dephasing, this process is also called as dephasing, is along xy plane. So we will see dephasing. So see, first the x-axis, then this is the circle where the dephasing will be going on. So slowly it goes to the every direction of the xy plane. The signal or the intensity of the bulk magnetization will be spread all over the xy plane like a circle. So this is the T2 relaxation, which is more, it requires more time. So this is the most important relaxation among the both. Now, so after attaining the relaxation process, what happens? So finally, the bulk magnetization will reach the z direction. So we get a signal. What is the signal called as FID? That is free induction decay. So you can see that one. So I am taking the intensity versus time, and the detector is placed at the x-axis. So the detector is seeing the intensity when the bulk magnetization is placed at the x-axis. The first time it has the highest intensity and slowly it decays. Slowly it decays. This is called as free induction decay. So the first point, what happens? Here the intensity high because all the bulk magnetization vector is present on the x-axis. Slowly the x-axis bulk magnetization vector is spreading to the z-axis by two processes of relaxation called as T1 and T2. Therefore, what happens? The signal is slowly decaying at time. Therefore, this is called as free induction decay. And the detector will record this free induction decay in a computer. But what is the problem with this one? This is a intensity of time, or this is a graph of a time. We don't want the graph of a time. We need a peaks. Therefore, there is a program called as Fourier transform, which converts this time interval into the frequency. So this is converted into frequency. Suppose the sample has many number of nuclei. So one nuclei has given this FID, the second nuclei has given this FID, and the peak will be coming for this one. And the third nuclei will have is another FID, so third peak will be coming. Like this, the Fourier transformer will convert all the FIDs present in a molecule or which is received by the detector into the graphical representation, which we easily plot it in ppms. Okay, so this is called as Ft-NMR spectra. Okay, so like this we can get a spectra of Ft-NMR by converting the time domain spectra into the frequency domain spectra by using a Fourier transformer method. It's a mathematical expression basically. So this is used to convert the spectra. So how this whole experiment will be going on? Just look at it. So for a 1D, that is NMR pulse sequence, there is an acquisition time called as FID. So this acquisition time, or where the signal is recorded, is called as acquisition time. This signal acquisition time is depends on the T2 and T1. If the T2 is longer, very good FID will be present and good resolution of the spectra will be appearing. So first thing is the preparation. So where we prepare our sample and keep it in the homogenization mixture, or we keep it in the magnets, between the magnets, and allow it for some time to get into the homogenization. Then we apply the pulse. So now this is just a switch on and switch off. Here we switch on and here we switch off. This is called as 90-degree pulse, or otherwise it is also called as excitation. We just excite it by using the RF pulse. Now what happens? We get a FID, or also called as acquisition. So this is the acquisition time. So you can see this is the FID, and this place between the FID is called as acquisition time. So now this is detected, this is recorded in the recorder, and we get here is the recorder, and this is the detection of the signal. So like this we can detect our Ft-NMR. Thank you for the patience listening. If you have any doubts, please post.